Okay, so there's a special form of energy, or there's a special form of energy associated with moving fluids. Okay, so fluids that are moving from one place to another possess a quantity known as flow energy or flow work. And it's essentially it's related, or can be illustrated at least, using an example very similar to what we were talking about um, uh, in a previous video when I was illustrating the concept of boundary work. And so the fluid itself acts to push itself along. Okay, and to illustrate this point, you can imagine a piston. If we segregate a small little block of fluid, we can imagine the fluid behind it acting as a piston. So this fluid is flowing this direction. The fluid in the block is being pushed into the system via an imaginary piston, which is basically constituted by the fluid behind the volume. So we have the fluid that's contained within this little volume, and it's being pushed along by the fluid behind it. So when fluid is moving, it possesses this flow energy or flow work. All right, and so just like before, the work is going to be equal to the force times the displacement. Okay, and we can break this back up into the pressure times the area for the force. That's times the displacement, and that's equal to the pressure times the volume. So the pressure times the volume of this of the displacement of this imaginary, the amount of displacement required to push this fluid contained in this segregated little block into our system is equal to the pressure of the fluid multiplied by the volume of the fluid that was displaced into the system. Okay, and this works for any. I'm going to show you here in a second, but it doesn't matter how small this goes. So in the limit, this becomes sort of like a continuous quantity. All right. And so I can express this in a per unit mass basis. And I get so pressure just comes along for the ride, and then the volume per unit mass is just called the specific volume, if you remember. And so specific volume is if you remember, the total volume per unit mass, and it's illustrated with the lowercase v. I use this crossbar here to distinguish volume from velocity or other. There's a lot of V's. You're going to see a lot of V's in thermodynamics and fluid mechanics. So if it gets a little crossbar like that, then it's volume. All right. Now, just briefly, a specific volume is total volume divided by mass, and density is mass divided by the total volume. So the specific volume is 1 over the density. And this quantity that is the product of the pressure times the specific volume is called, is the flow work. And you see both the pressure and the specific volume are intrinsic properties, right? So this is a property of a moving fluid. Okay? And so we have to account for it when we're dealing with moving fluids. So how does this relate to, if you remember from, just the previous video, we were dealing with the fully written out energy balance equation. I probably didn't express that this is actually, that's what this is called. So the change in, I want to write it in rate form. So we're only going to be dealing with mass flow in terms of when fluids are moving into or out of a system or control volume in a sort of a continuous fashion. You have a piping system, it comes in through a pump and goes out. We're never going to be dealing with a block of block of mass being deposited into a system, without respect to a rate or something like that. So when we're dealing with energy transfer via mass, the only time you're going to see that in this class is when that mass is flowing in a continuous rate. And so the energy balance in that case, in rate form, if you remember, is given by the time derivative of the energy of the system is equal to the rate at which the energy enters minus the rate at which energy leaves. All right, and so let's just write this all out explicitly. So we get heat, work, and mass flow. All right, and then if you want, the rate of change of energy of the system is going to be the same as the rate of change of the kinetic energy plus the rate of change of the potential energy plus the rate of change of the internal energy. Okay, and we've already sort of discussed what heat and work was. So the energy via mass flow, this term theta, is going to be the energy of a moving fluid per unit mass. And this is the only place you'll see it expressed. You'll only be, so everywhere you see a theta, you'll see it multiplied by by a mass flow rate. Usually, unless we're canceling all the mass out of a system for some reason or another. But it has to be, in order to have units, so this has units of, say, joules per kilogram, or kilojoules per kilogram, or something like that. All right, and so theta is equal to the internal energy of the fluid per unit mass plus the flow energy plus the kinetic energy plus a potential energy per unit mass. And so the internal energy per unit mass is given by lowercase u. The flow energy per unit mass is the pressure times the specific volume plus the kinetic energy per unit mass plus the potential energy per unit mass. And so that equals, we're going to group these together here. I'm just going to put the parentheses in there and we're going to group these together in future lectures. So I'm just going to go ahead and preempt that with a grouping like that. So these are all properties of a fluid, right? And then the kinetic energy per unit mass is just 1/2 v squared. So that's a property, associated with how fast the fluid's moving. That's where v is speed. And then because we're only interested in gravitational potential energy, this is just gz. All right. Remember, if I wanted the total kinetic energy, I'd have to multiply this by the mass, but I'm talking about kinetic energy per unit mass. So this is what theta is. So here we have a grouping of individual properties of the fluid, intrinsic properties of the fluid. So if I can know the state of the fluid as it enters the imaginary piston, because if I know 2 of these properties, I know the state, right? So if I know 2 of these properties, I know the third, or if I know the state of the system as it enters the thing, as it enters the system or control volume, then I know all these properties. But they're only state properties, is my point. These are properties of the fluid. This relates to how fast the fluid's moving, and this is, related to how far it is off the datum plane or the ground or whatever it is you're going to use for the elevation. Okay?